So, having seen the conditions for regularization etc., where we would like to optimize further from the optimum solution that we have to be able to approximate our so instead of having every instead of having a hidden unit that corresponds to every point in the data set, we can reduce this complexity by having an approximate solution, right. So, we do not use all the data points, that is we do not have the number of hidden units that equals the number of data points, and we would like to solve the RBF problem, the radial basis function network, and arrive at the optimum weights. So, let us see how this can be done. So, we will consider the radial basis function networks as a special case of the Green's network. Let us consider the pair of Gaussian functions we have g of norm of x minus ti is exponential minus norm x minus ti, the norm square for I equals 1 comma 2, and let us choose centers at T1 and T2, where T1 is 1 comma 1 transposed and T2 is 0 comma 0 transposed. Okay. So, at the moment you forget the optimization over choices of T1 and T2. So, at the moment so I told you earlier that you could set up the Tikhonov functional and then you could optimize T1 and T2 also along with your regulatory conditions. So, at the moment we are not bringing regularization, we are not also bringing optimization over T1 and T2, we assume some choice of T1 and T2, and assuming this, let us try to solve the XOR problem. Now, my y of x equals summation I equals 1 to 2 the weights connecting the Green's units in the hidden layer with the output plus this bias. Now, y of xj is dj, where dj is my desired response and we have 4 data points in the XOR problem, right. So, let me write down these details. So, this is my data vector xj and I have my desired dj, it's 1 comma 1, 0 comma 1, 0 comma 0 and then 1 comma 0. My desired is 0 1 0 1, that is my desired. So, the way this network looks is as follows. I have inputs x1 and x2 2 coordinates because it is a 2 dimensional vector. So, xj belongs to R2, it is a 2-dimensional vector. So, I have 2 hidden units. And these are my phi 1 and phi 2, right. I look at all possible connections from the inputs to the hidden nodes. And then I have my weights that I am using to combine these nodes. And because this XOR problem is sort of symmetric, I can assume that there is weight sharing. I have the same weights W, and I have a bias that is added to the output, right, and this is my output. Now, I have everything defined here. I know what my DJs are, my unknowns are W and B that I need to solve, and I can evaluate this Gaussian unit as a function of my data points x, and given that I know what TIs are for I equals 1 and 2, right. So, I goes from 1 to 2 and j goes from 1 to 4, right. This is I here, and this is the j where I have data points that I have to stream. So, maybe I will put this j corresponding to n xj here, so that it is compliant. Now, what I need is I can form my Graham matrix. So, I have this to be a 4 by, so you can imagine this to be a 4 by 2, plus I augment it for the bias, and it is going to be a 1 1 1 1 1 1 1 here in the last column. And when I do the evaluations over the submatrix 4 by 2 comprising of 4 data points and 2 centers T1 and T2, right. You can cross verify. Okay, so you have this in this form. My D vector is 0 1 0 1 transposed, which is this 4 by 1 column vector. My weight vector is W W and B transposed. This is a 3 by 1 vector, it is a 4 by 1. Now, what I have to do is solve this equation, which is W given by G transposed G inverse G transposed D. This is without regularization. If I want to bring in some regularity conditions, then I have to put this lambda G naught, and I have to choose my lambda appropriately. So, solving for this equation, that means you plug in G and D into W, from numerical computations done earlier. You can verify that this weight vector is going to be minus 2.5, minus 2.5, and this bias is going to be plus 2.84. Okay, and this is consistent with what we have, right. So G transpose is 3 by 4 and this is 4 by 3. So you will end up with a 3 by 3 times a 3 by 4 times 4 by 1, which is going to be your 3 by 1 vector, which is what you have for W. So now this is our network, right. Once you solve for W, you get these parameters and you choose this these parameters in the output of the network, that is for the weights connecting the Gaussian units to the output node, and with the choice of the bias that you have, you can solve the XOR network, right. This is the solution to the XOR problem. So what we have done is we have illustrated how you can solve the XOR problem using an RBF network, but instead of having a hidden node that corresponds to every data point, I choose my centers T1 and T2 appropriately that I can use in my hidden units, and thereby I set up this problem and then I can solve for this problem using the RBF network. So I think this hopefully should illustrate, this example should illustrate how you can go ahead and set up the network and solve for the network parameters based upon the data and the desired response that you have. And if you want to impose any regulatory conditions, you can do so as well, and then solve for your network parameters, your neural network parameters. Okay. So with this illustrative example, I hope you will be able to take this towards practice, where you may have really huge data sets and then you can consider various forms of optimization in your problem based upon this toy example that we discussed. Okay. So we shall end this here, and we will next consider the regularization problem, based for, I mean, we will consider the regression problem based on regularity conditions, right. We will consider the regression problem based on regularization constraints.